So just testing, okay, everybody can hear me? Awesome. Yeah, as Siamak said, my name is Mark Shaw. I'm a hardware engineering manager at Microsoft. I like to maybe emphasize on the engineer over the manager, which means that they only let me out to publicly speak about once a year. So we're going to talk today about our Flash expansion box. It's on demo out at the Microsoft booth. About 1 year ago, we introduced this at OCP in a kind of a partnership with Facebook on the concept. It had a number of goals. You know, we wanted something modular, a PCI expansion chassis that's modular, kind of enabling the next generation Flash technology. If we kind of looked out there, there was nothing really hot swapped, right? There was nothing for the data centers for a hot swap that provided any type of density. So we were looking for something optimized for NVMe hot swap, and we wanted something that was head node agnostic, right? You've seen kind of Project Olympus supports a number of processor families in a very common form factor. We want to give our end customers the ability to hook up whatever they want to for it. So, you know, we looked at putting this, you know, all inside one chassis, but then you start thinking about as generations roll, holes move, and you end up having a very difficult time maintaining latest technologies with it. So we want something that was modular, because we felt like that would give us, you know, a good 5 to 7 year life cycle. We wanted to kind of leverage all of the Mount Olympus building blocks. We don't want to recreate the wheel on a lot of things. So we wanted to maintain our current existing power supplies. We wanted to maintain our existing fans. We wanted to be able to just kind of drop this into our sheet metal as much as possible because, you know, it's all about time to market. And then we wanted to kind of leverage as much of the OCP community as we could. This was a really, you know, Lightning provided a great jumping off point for us. They had already blazed a trail with switch technologies. They had blazed a trail with hot swap. And then, you know, since we have kind of a pretty good relationship with Facebook, we were able to partner with them and kind of leverage that architecture going forward. We wanted to, we also found that, you know, by partnering with them and using some of the OCP stuff, we didn't have to recreate PCI retimers. We were able to export all of our PCIe out of the box. We just have to go to a vendor and say, hey, this is what we want. We didn't have to design it, which is, you know, a huge help for engineers because we don't like to do things that people have already done. We wanted to build something that was adaptable to the open rack and to the OCP community. So as you kind of look at it, you can kind of imagine, you know, hey, it goes into our 21-inch rack, but it's very portable to going into a 19-inch rack. You know, at the end of the day, what's the difference between a 21-inch rack and a 19-inch rack? What's the difference between OCP racks and our racks? It's still 12 volts is the primary, you know, voltage going in. As long as you place things correctly, things are fairly portable between the designs. And we wanted to kind of, we were kind of eyeing this with a look at future Flash technologies. If we kind of, Microsoft is very M.2 centric, right? We install a lot of M.2s in a lot of things, but we couldn't necessarily count on the fact that M.2 was going to be supporting all the Flash technologies that we wanted coming up. And that kind of leads us a little bit. So a brief look at the original chassis concept, and this chassis concept lived really. We didn't have to really remake it quite a bit. It's basically a Microsoft Project Olympus chassis. It uses our power supply, N+2 fans. We bring in 2 PCIe by 32, 2 by 16 lanes, cabled from an external host into this modular box. From there, that PCIe is cabled internally back to a switchboard, and from there, the PCIe is exported from the switches in by 8s to all of our Flash, or we just call them, you know, storage carrier modules. It's not a particularly fancy or even complicated architecture. It's a very simple architecture. I think the key for us is the front technology, which is the storage carriers and what we put in those. We started with an original M.2 carrier concept, which was a kind of a toolless, 1U tall, about a foot long. You know, some people would say it's about the length of a ruler. The original concept was we can put 4 M.2 modules into this. We can port PCIe by 2 to each module. We can support something along the lines of maximum power of 50 watts with a toolless serviceability. So again, we're thinking at the time very M.2 centric, but we were trying to have an eye on what might be coming up. And after we presented this, that what might be coming up kind of jumped at us, right, in the form of a group called EDSFF. So this was the Enterprise and Data Storage form factors. So this was a group that had already was talking about next generation storage. They were talking about how do we do flash hot swap in the data center. Intel at the time had released some product concepts. Those product concepts looked very similar to what we were doing. So, in Reese's terms, our peanut butter met their chocolate. And we ended up joining that community. Now, if you've ever been part of a industry standards body, it was the first day is a wonderful marriage. The second day, the arguments start. And I kind of describe it as industry standards as you're trying to push a glacier with a noodle. And everybody's arguing about the direction the glacier is going. And everybody's arguing about the specification for the noodle. But it was a wonderful group of people, very dedicated to doing this. And within about a year, we had generated a connector specification that's released to SFF TA1002. It's a by 8 connector, keyed with by 4 support. So it supports, and the nice thing about it is, we're all stuck in today, but we all have seen Gen 4 coming, PCIe Gen 4. We've all seen PCIe Gen 5 talked about. We're all scared to death of Gen 5, but that's the way it goes. This connector, signal integrity-wise, supports Gen 3, Gen 4, Gen 5, possibly beyond. It's by 4 and by 8. We have already concepts expanding it to by 16, and we're talking about concepts that expand it to by 32. It supports 12 volts and can support up to 50 watts, depending on how much air you're willing to blow on it, beyond 50 watts. So it gave us something that we could standardize on, that gave us future proofing. And beyond that, it was something that we found we could share with other bodies, right? There was a number of members on that committee from Gen Z. So we worked with Gen Z. The pinout for this, if you plug something from Gen Z into this, it'll work. If you plug this into, we use the same standard on the OCPUS18 3.0 card. Kobo adopts something very similar. So this connector technology is propagating, and which means wonderful things for us, which means that we're going to have second sources, right? Second sources are already licensing and lining up for it. And this thing is optimized for hot plug. So when we talk about hot plug, I think a lot of people are nervous about us plugging a connector. I will say it's a managed hot plug, right? Which means that when you plug it in, things aren't instantly on, right? It detects presence, then it organizes the turn on of that slot. 3.3 volt standby comes on. Then a PCIe switch recognizes that it's there, and the PCIe switch turns on 12 volts. So you're never plugging in to something that's already hot, right? We call it a managed hot plug. So after we got the connector done, which was a long, arduous task, that was probably the hard part. The form factor is probably actually a little bit easier. We all knew approximately what we wanted. It was a matter of ironing out the details. But what we did was we factored a form factor, the EDSFF 1U long, 18 millimeter. There's a few different variations in the family, right? There's an 18 millimeter, or a 1U 9 millimeter, which is nice and thin, and you can fit 32 of those in a box. Then there's a 18 millimeter wide one, which is a little bit wider to support higher form factors. So for us doing an M.2 carrier, this form factor, we were able to craft this form factor in our M.2 carrier and do the exact same thing so that we are electrically compatible and 100% physically compatible. So whether you're plugging in an EDSFF 1U long or you're plugging in an M.2 carrier, they're both the same to us. So this is bringing in just a higher power version of the 1U long. And one of the key for us is that by going with EDSFF, we enabled some next generation flash technologies. What we found was that as certain flash technologies such as QLC came along, the controllers grew to the point where they weren't going to fit on M.2s. So adopting a standard beyond M.2 is enabling us to basically give our end customers, partners, a lot more flexibility going forward to choose the solutions that make sense for them. And this supports 48 plus NAND sites. So I won't comment on the density, but it's very dense. One of the next changes that came about was Project Cerberus and the idea of increasing the boot security of our devices, right? So basically, Cerberus is this FX16 box is our lead vehicle for Cerberus. So it's the first one to boot BMC with our Project Cerberus technology. What we have right now is just a proof of concept security module that is basically blocking any attempts to corrupt or write unauthorized access to the flash, as well as authenticating any flash that's any firmware that's on it. And this is kind of the first step in enabling a common security platform across all of Project Olympus. So this will show up on, it first shows up on FX16, and then it'll be on our it'll start showing up on next generation processor boards as well. So last slide, because Siamak only limited me to 10 minutes. How real is it? So we've got hardware demonstrations available. You can see this out at the Microsoft booth. I didn't show really any pictures of the carriers, mainly because we have them. Right? You can go out, you can hold, you can touch, you can feel. They're actually quite nice. You can plug them in and out. So they are real. We are currently at about EV-DV stage. We are testing with them, and things are going quite well. So visit us at the Microsoft booth, or you've probably seen press announcements from our partner WeWin, who also has them at their booth. And that's my presentation. Any questions?
With the difference between the monolithic and then the carrier, I assume you're not doing anything on the back end to concatenate the 4M.2s into a single storage device, as if you went with the EDSFF long, that would be a single device.
So since we're going through a PCIe switch, we can bifurcate the switch to by 2, so the M.2s appear as 4 storage devices. If you put an EDSFF in with a by 4 interface, it'll appear as 1 storage device. So does that answer the question? Yeah. Okay.
Would you also comment about the cable connection between the two?
The cable connection between the
Between the chassis and the server?
Oh, certainly. So it supports 2 PCIe by 16 lanes, which can bifurcate down to by 4. However, our customers want to bifurcate to get the best performance. I'm assuming they're going to bifurcate to by 4. And from there, each by 16 feeds 1 switch, and then that switch feeds 8 M.2 carriers.
Yeah, my question is also about the cables. Does the 2 cables actually connect to the same server or 2 different servers?
So that's maybe a SKU-specific question. So I think within our concept, they would connect to the same server, but there's nothing that limits you to that. They can be operated as 2 separate domains. We did actually put in the links, put in the traces for cross-links between the switches. So if eventually we want to evolve to where multiple nodes are sharing memory, we can evolve that.
One of the major things that we are proposing here is these are all concepts for you guys to use and add on. So use it the way you like. It is capable of either way. The way Microsoft uses it might be very specific, but another customer might want it a different way.
Good. All right.
Any more questions?
On to the Master of Ceremonies.
Okay, thank you very much. We move on to the next topic.
Good job. Kill him.
Okay, we started with the servers. Then each server was only 1 U, didn't have much expansion capability, so we needed to have expansion chassis. One of the expansion chassis we talked about was a JBOD, and Mark just mentioned a JBOF, just a bunch of flash. The next topic will be a chassis that has a lot of GPUs in it. So the foundation for a lot of work that we do with Project Olympus is to take advantage of the infrastructure that we have built. We wanted to have an open source hardware, inviting collaboration from others, and use industry standard components so interoperability is possible. Fuel innovations from others, collaborate, and build better products. Starting with Project Olympus Foundation for rack, power management, And rack management infrastructure was a foundational element for this expansion box that we wanted to use so that we can fit this expansion box into the data center more easily. So you've seen some of this before, so I don't need to repeat that. The design target for this expansion box, as we have described before, was 8 NVIDIA SXM2 processor GPU modules. The newest version of that is the Volta 100 SXM2 running at NVLink at 25 gigatransfers per second. We also needed a CPU complex to go along with it. So Project Olympus motherboard built by WeWin was a very good, suitable solution for that. All we needed to do then was to have a chassis for an expansion box. For that, our colleagues from Ingrasys helped out. So the combination of NVIDIA GPUs with Ingrasys chassis and WeWin motherboards for Project Olympus Blade chassis was a starting point for us. We presented this one last year, and this year we're talking about some updates. We have talked about these chassis interconnecting to each other. In the case of the JBOD, the reasonable interconnect would be SAS cable. In the case of JBOF, FX16, we're using SAS, mini SAS cables, but we run PCIe through them. In the case of an expansion box such as this, having very many external cables seemed hard to do. So we have come up with a way to use internal cables inside the chassis without stiff bend radius and interconnecting using by 16 cables to the same host node. The host node in this case is the same motherboard for Project Olympus. So this Faraday cage that you see hides all of the EMI problems and makes it at least look nice. But a 2-socket server sometimes is not sufficient to fuel all these GPU capabilities. So other colleagues from Inspur collaborated with us, and we came up with a 4-socket solution. And since the chassis was designed for cascading multiple chassis together, up to 32 GPUs is possible. And this is an example of how the same cabling allows a processor complex such as Inspur's 4-socket unit interconnect through 4 other expansion chassis. You could perhaps see and spot some of the cables underneath those Faraday cages. Okay, so hardware by itself is not sufficient. You have to have some applications, very suitable applications for these wonderful NVIDIA GPUs are video transcoding, HPC, artificial intelligence, and CNTK, Cognitive Toolkit from Microsoft is a good framework to run all these applications. A variation of this chassis can support regular PCIe cards. For example, NVIDIA GPUs of different kinds can plug in. The PCIe topology and interconnect topology between the GPUs, NVIDIA has published these before. I'm just repeating this. In this particular case, the baseboard for SXM2 modules supports 6 NVLink cables, 6 NVLinks running at 25 gigabits per transfer. Within a rack, we need to bring power to the chassis, and we need to manage them. So using other ingredients from Project Olympus, what we have already contributed, a standalone rack manager is suitable as compared to the PMDU that you have seen in a spine model. This is a standalone chassis that can support a chassis that does not have the Microsoft Olympus power supply. Other ingredients that helped us build this chassis and put it together with a processor head node was small riser boards to extract PCIe cables from PCIe slots, and a little module to allow PCIe cards to plug into the baseboard. We have published these topologies before. You could think of one of the expansion chassis as a complex of PCIe switches interconnected, and private interconnect within the baseboard is NVLink, but external cables are PCIe. You can combine them together in using cables that I showed. One processor head node can connect to one expansion chassis. Because the expansion chassis has 8 by 16 cables and the PCIe switches are capable of multi-hosting, it is conceivable for you guys to put together a solution that multiple processor head nodes can talk to one chassis. Or you can put them together in a larger formation that one host can be interconnected to multiple chassis. Different topologies are possible, and if you guys have great ideas, we'll put them to work. Our researchers are very excited about these solutions, and there are a number of companies around that are building software solutions around moving data across these cables from switch to switch. So to highlight and summarize these features, the chassis is a 4U chassis. It has off-the-shelf power supplies. These are not Project Olympus power supplies. These are the ones that you take C13, C14 cables. But the rack manager that I suggested earlier and another power adapter module that you can see it in the booth combines to be able to plug these things together with regular power processors and other head nodes. The cable, we have changed it from last year. Last year we were using a different cable. This time we're using, we have learned from feedback that we received, and we are using TE's sliver cable connector. We work with our colleagues to perfect that. There are 4 PCIe slots available for full height, 3/4 length. Could be used for InfiniBand or networking, other networking. The BMC for this is actually running OpenBMC. That's another innovation that we're bringing into our Project Olympus, working with the community on OpenBMC, and that's another example of that. As I mentioned, the main target for this chassis was Volta 100. However, using the PCIe mezzanines, we can plug in other PCIe cards. A number of those are possible. The thermal envelope is based on 300 GPGPUs. There's tremendous bandwidth available between chassis through by 16 cables. You can have them connected using fabric mode, and there are a number of companies who are building management processors for fabric mode to allow peer-to-peer communication at PCIe Gen 3 bitrate. So the chassis that is targeting artificial intelligence. This is a hyperscale suitable. And we have a number of these specifications contributed to OCP. You can find them on OCP websites. We invite collaboration with others. As you noticed, it's a combination of work with others. If you have different ideas, different feedback, please provide. Our researchers are very excited in running different workloads and different interconnects. You can find all Project Olympus material on the wiki pages that we have on OCP. You can participate in Project Olympus subgroup as part of the server project of OCP. Please come and help. So add value to whatever we're doing. Help your colleagues. We can build products. These products are all ready and ready for sale. Any questions either for me or for Mark? We can come back and answer some of the questions.
Okay, sorry. I do have a few questions. The first one is for the unveiling GPU. Do you have any real application deployment using multiple heads sharing one GPU box? That's my first question. My second question is for the except the unveiling GPU box. If you have multiple heads sharing the same GPU box, how do you solve the data sharing problem? Because the unveiling between the GPU, you have the problem. For example, if you have the one head for one server for one customer and another head for another customer, the NVLink between the GPU would not you would not be able to disconnect it. Right? You may have some data leaking or any other potential issue. How do you solve this problem?
Okay, so I can address it two ways. One is the whole chassis can be used for one VM. In that case, there is no confusion about multi-tenancy. The multi-tenancy can be resolved in hardware. Certain NVLinks could be turned off from the beginning, or it could be done by the hypervisor, or an equivalent or a hypervisor. It could be containerized. PCIe switches help isolate PCIe links. NVLinks can be turned off from the beginning. And there is a mechanism that NVIDIA has produced for multi-tenancy as well. So Robert is here. He can talk to you about that specific from NVIDIA, or you can talk to us later. We can elaborate. It's a tough problem. Multi-tenancy and security and privacy is important, and we do have solutions for that.
Good morning, Siamak.
Happy New Year, by the way.
Happy New Year.
Okay.
Thank you. The question I had for you was that obviously in a typical data center, you have something in order of 100,000 to maybe 500,000 servers. And given that it looks like to connect to a GPU, you almost have created sort of a back side network connection from a PCI Express to the GPUs. I mean, do you distribute these GPUs on every rack, or do you provide connectivity to all of the servers? How do you, how do you reach this, GPU, or do you only have GPUs located in a specific portion of data center which is doing a specific type of work?
Okay. I will cut it into two different questions.
Okay.
One question for me as an OCP
Yes.
colleague.
Right.
Another question as for me as a Microsoft
yes.
Customer, perhaps,
That's
right?
right.
So, okay. So, OCP, I need your help. So, solve the problem.
Right.
Microsoft, we have our solutions. We are limited, basically, based on the physics of what we're doing in our data centers. Mm-hmm. Not every rack can have too much power. our power per rack is limited. So when we have a chassis like this that uses more than 3 kilowatts, 3.5 kilowatts, there are not very many of those racks chassis you can put in a rack. So you will be limited by the power per rack.
Right.
Because of that, it limits the trouble of interconnecting them. So if you need to interconnect very many chassis, then you will have to have many different racks.
Right.
And as you know, across rack, you need to cable them using something useful. InfiniBand is a good choice. Other people use Ethernet. Rocky is a good choice.
Right, Rocky, okay.
PCIe that I mentioned is good within a rack. We have not endeavored to extend that PCIe connectivity across the rack. However, other people have proposed, again, I need your help. Other people have proposed to even have repeaters and retimers that have optical cables to even extend PCIe reach. But if it is necessary or not, there's the management, there's cost, there's ecosystem work that needs to be done.
Do you think that putting, like, for example, using Rocky and putting one GPU, you know, in every one of the rack, is that a practical solution that you're looking at, or?
People have demonstrated that Rocky can be useful for scaling out GPU boxes. There are a number of papers. Actually, Facebook has a very good paper on that as well.
Thank you very much, and Happy New Year again.
Sure. One more question, and then Laura is waiting for us. Any other question on expansion chassis? Yeah, okay, thanks. Yeah, we can take a couple more questions as Laura set things up.
So you've packed a phenomenal amount of I/O into this box, but in any computation problem, there's going to be some bottleneck. If you look at the complete problem of getting data off the persistent store into memory to the GPU and back, where are the bottlenecks in this solution?
Let me just talk about the capabilities, and I need your help to fix all the bottlenecks. So if we have, we talked about different server nodes today, and we talked about different expansion chassis today. So what we have tried to do is that if each one of these expansion chassis provides 8 by 16 PCIe links for external connectivity. The external connectivity can be storage, and storage could be on PCIe. In addition to these 8 PCIe links that are available for private connection, there are 4 by 16 PCIe cards also. So depending on how far of a reach you want to have to the networking system, to the storage system, or to the adjacent server, you can use either PCIe cards through networking mechanisms or PCIe cables using the local interconnect. Thank you very much. And I will give it back to Laura Caulfield. She is going to talk about Project Denali. It's a lot of exciting things to talk about.
Yeah, got quite the crowd out there.
Thank you very much. Thank you very much, Mark.